Okay, so in our last video for 5.2, inverse functions, we're going to start by looking at the problems that you were given at the end of the third video. And if you had gone through and found the inverse functions correctly, you would have found that these were the solutions. So for our first function, there's a couple different ways you could have written that one, depending on how you dealt with that negative in front of the negative 5. But those would be acceptable for the inverse function for A, and then for B, we can see the inverse function is written there. So if you had trouble with those, go back and check out the videos again and see how we work those to see if maybe that helps a little bit. But what we're going to do now is we're going to continue the idea of looking at how to find inverse functions, but in particular we're going to look at the issue that arises sometimes where either our function or our inverse function are not naturally one-to-one, which might lend itself to troubles in terms of it being an inverse, but we have ways of working around that. So here what we're going to consider is if we're trying to find inverse functions, and if f or f inverse is not naturally one-to-one, how do we deal with this? Well, let's start by considering an old friend. This is a function we've dealt with a lot. So this is just f of x is equal to the square root of x. And what we're going to want to do here is, it's a simple example, but we can work through these three important steps of finding f inverse, graphing the two together, and then identify the domain and the range of both. So really kind of putting together all of these skills we've assembled over the course of this series of videos. So let's start with part A here. So we've got to find the inverse function. Well, we know how this works. The first thing we've got to do, step one, is we want to see if the square root of x is a one-to-one function. Well, off to the side here, just so we can visualize this, I'm just going to sketch a quick graph of the square root of x. And as we should know, the square root of x looks something like this. So we've got a point at the origin, and then we have a curve that looks like this. So looking at this, it seems pretty clear that we've got a one-to-one function because it passes the horizontal line test and would therefore be invertible. So in terms of part one, yes, we've got a one-to-one function. And then we just go through this process. So the first thing we do is we take our function, the square root of x, we set it equal to y, then we go through and we swap our x and our y's, and then in step 4 we have to solve for this. Now, here's the whole purpose of the inverse functions. We're trying to solve for y here, and we need to figure out how we can undo the square root. Well, to undo a square root, as we know, what we're going to do is we're going to square both sides. So if we square both sides here, what we see is that we have y is what's left, and then we have x squared. This is our inverse function. So this sort of points out why we need inverse functions, is they help us solve these equations. You know, we wouldn't be able to solve radical equations from 5.3 if it's not for the fact that we've got these power functions like x squared or x cubed to help us undo the radicals so that we can isolate the variable that we're after. So here we found out that our inverse function is going to be x squared. This is where we're going into a little bit of trouble though, because if our inverse function f of x, or f inverse of x rather, excuse me, is this one-to-one? Well, let's go ahead and sketch what we would see here. So if we were to graph x squared, we know that this is a parabola. And if we were to think about this, well, is this a one-to-one function? Clearly it's not, because if we were to draw a horizontal line in multiple places, this fails the horizontal line test. So it fails the horizontal line test. So it's not one-to-one on its natural domain. And the natural domain of x squared, if we were just looking at it by itself, the natural domain is all real numbers from negative infinity to positive infinity. So here's what we're going to do, is we're going to kind of fudge this a little bit, and we're going to say, well, yeah, maybe the whole function x squared doesn't pass the horizontal line test, but what if we restricted the domain here? So if we restrict the domain, and what do you think would be an appropriate restriction? So we want to restrict this just enough so that it's able to pass the horizontal line test. Well, what I might suggest here is that let's go ahead and just conveniently ignore that negative side of our parabola. And if we restrict the domain, we could restrict it to just x is greater than or equal to 0. Well, now it's 1 to 1. So now y equals x squared is 1 to 1 if we only consider those x values. So that's what's going to help us here. So if we go back to our problem here, we're going to say, well, maybe not on, it's not 1 to 1 on the entire real number line, but f inverse of x equals x squared, where x is greater than or equal to 0, is 1 to 1. So this, and we have to include that condition on x, that would be our inverse function. So that's an example of why we need to sometimes restrict the domain in finding a function and its inverse. Okay, so that was part A. For part B, we're going to want to graph these two together. We've kind of already gotten a pretty good start here. So let's just put this over here for part B. If we draw our axes, so we've got our x and our y. So I'm going to do the square root of x here in blue. So this is f, and then in green I'm going to do the f inverse of x squared, and this would look, again, we're only using part of this, but we could see how that works out. And again, we notice the symmetry, so this would be f inverse. And as we would expect, as we talked about in the last video, it has this symmetry where if we were to draw the line y is equal to x, these two curves, I didn't quite get it perfectly, but so I apologize for that, but we've got a symmetric curve. So if I picked any point on f inverse, it has a symmetric point across that line right there. So we can see that importance. And then lastly, we'll identify the domain and the range of both. So why don't we put this next to our curve. So for part C, well, for f of x is equal to the square root of x, we know that the domain, well, we could do it a number of ways. We could look at the curve and we could see, well, it only exists from 0 on out. Also, we could consider just the square root of x. We know that we can't take the square root of negative numbers. So the domain of f would be equal to x being greater than or equal to 0. And if we look at the graph, or we consider the range of a square root function, we know that this function is always going to be greater than or equal to 0. It doesn't exist below. If we were then to look at f of x, the inverse of f of x being x squared, where x is greater than or equal to 0, we've already got our domain implied here. So the domain of f inverse will be x is greater than or equal to 0, and the range of f inverse will be y is greater than or equal to 0. Now this is a kind of a tricky example because it ends up being the same for both, but we do see this characteristic of inverse functions where the domain of f is equal to the range of f inverse, and the range of f inverse is equal to, or the range of f is equal to the domain of f inverse. Unfortunately here they're both the same, so it's not quite as distinct, but I think we can check that out in a second example here. So let's go ahead and try another example. So in this example, we're going to do the same approach, except we're going to consider a different function. So let's say given that f of x is equal to the square root of, let's say, 3x plus 1. We're going to want to find f inverse. We're going to graph both together. And lastly, we're going to want to identify the domain and range of both. So hopefully this will be a better example to sort of go through this. Okay, so let's go through the process of finding the inverse. So finding f inverse of x. So we start by asking, is f 1 to 1? Well, let's sketch this to see if it passes the horizontal line test. And if we were to graph this curve and think about what this graph represents, we've got a radical function, square root, that has actually been shifted to the left here 1/3 of a unit. So what our curve ends up looking like is something like this. And again, square root function, so it's going to be 1 to 1. So we can say yes. We can check this off. So if we go to step 2, now we go through the process of solving this. So we'll take the square root of 3x plus 1, and we'll set it equal to y. Then we'll go ahead and we'll swap the x's and the y's in step 3. And then in step 4, we'll go about solving this. Well, the first thing that we should do, again, as with the last example, let's go ahead and square both sides. So if we square both sides of this equation, we'll essentially be canceling out or undoing the square root here. So now we're looking at the term under the radical, 3y plus 1 is equal to x squared. And then let's just go ahead and we'll subtract 1 from both sides. So we'll have 3y is equal to x squared minus 1. And then lastly, let's go ahead and divide both sides by 3. So we get y is equal to x squared minus 1 divided by 3. Depending on how we want to look at this, it might be advantageous to think about it as x squared over 3 minus 1/3. We might be able to think about the transformations later on. Either way is perfectly fine. And this is going to be the algebraic representation of our inverse function. So now all we have to do is we've got to consider, well, is f inverse 1 to 1? Well, let's graph it and see. Automatically, you should start to get a sinking feeling about this because it's a quadratic. And what you're going to notice is that anytime you're dealing with inverses that happen to be quadratic functions, whether it be f of x or f inverse of x, somewhere along the line the domain is going to need to be restricted, because parabolas by definition are going to fail the horizontal line test. So this is going to be bad news for us, but that's okay because we know how to handle it. So if we go back to our curve, we've got our x and our y. If we were to graph this parabola, this is a parabola that's been slightly scaled and shifted down. So we can say that we know the y-intercept is going to be negative 1/3, and this curve would end up looking something like this. It's an upward-facing parabola with that y-intercept. So we're going to have to restrict the domain. So it fails the horizontal line test. So this tells us that we're going to have to restrict the domain. So we've got to take our fate into our own hands and make this a one-to-one function. So what we're going to do is we're just going to kind of ignore this half, and we're going to say that, well, if again, since this is centered on the x-axis, we're going to let the domain of f inverse be x values greater than or equal to 0. So if we go back to our original problem, we'll say that so f inverse of x is x squared minus 1 divided by 3, where x has to be greater than or equal to 0. And if we were to go through the process of graphing it, or graphing them together, we can see again how this symmetry plays in, because we know we've got x, we've got y, and we know that these intercepts are similar. So if we were to graph f, our original function, the square root of 3x plus 1, we know that we get something like this. And if we graph f inverse, which we've restricted now, we get something that looks like this. And again, both of these are symmetric across this line. Y is equal to x. Additionally, if we were to look at the domain and the range of these, we would see that the domain of f is going to be, let's look at this. So what x values does our function square root of 3x plus 1 take on? Well, it starts at x equals negative 1/3 and moves along the x-axis. So x has to be greater than or equal to negative 1/3. Additionally, we could consider that the function, if we plugged in any numbers less than negative 1/3, we'd have a negative under the square root sign. And then the range of f, again, it doesn't exist below the x-axis, so our y values are always going to be greater than or equal to 0. And then if we look at the domain of f inverse, well, we had to restrict it specifically to x has to be greater than or equal to 0. And looking at the range of this parabola, since it goes down to y equals negative 1/3, and then just continues upward from there, y is going to be greater than or equal to negative 1/3. And what we see is that the domain of f is the same as the range of f inverse, and the range of f is the same as the domain of f inverse. Okay, so that's, you got to watch out for these, especially with the quadratics. And I think that just about does it for inverse functions. Just as a quick summary, there's some key things that we've learned here, especially sort of the characteristics of inverse functions. So we'll call this a summary of inverse functions. We've done lots of examples, so those we'll want to make sure that we're clear on, and we'll do plenty more in class for this and in your homework. But some things to keep in mind: that the summary of inverse functions, we know that both f and f inverse must be 1-to-1. We also picked up when we first looked at this that the compositions of f and f inverse equal x, so they undo each other. And we also looked at some interesting symmetries, that we know that the graphs of f and f inverse are symmetric. across the line y equals x, which makes sense because the y is equal to x. We did this in solving the equations. We exchanged, or finding inverses. We exchanged the x and the y. The domain, the x's are equal to the range of the other. The x's are equal to y. So this is a common theme with inverse functions. And lastly, we know that the domain of f is equal to the range of f inverse, and the range of f is equal to the domain of f inverse. So that's a quick summary. Thank you guys for watching the videos, and I'll see you guys in class.